Hai, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give an introduction to the idea of the dot product and some of its properties. Well, so far we have added two vectors and we have multiplied a vector by a scalar. So the question arises whether it is possible or not to multiply two vectors so that their product is a useful quantity. Well, the short answer is yes, and there are two types of multiplication arise here, which is the dot product and the cross product. So let us talk about the dot product. If vector A is defined as A1, A2, A3 and B is given by B1, B2 and B3, so these are three-dimensional vectors, then the dot product of A and B is given by this formula here. So this is the dot product, A multiplied with B, and you will get A1 times B1. So basically you are multiplying with its respective component, A1 and B1, and A2 with B2, and A3 with B3. And once you have all that, you just add them up all together. So note that the result that you have here is not a vector, because when you continue with the process, you will get with one single number. So it is a real number, and it's also known as scalar, and for that reason the dot product is sometimes called the scalar product or inner product. Okay, let us go through with some simple examples to illustrate the idea of the dot product. Okay, so the first one is you have a two-dimensional vector 2, 4 and 3, -1. So we're going to multiply them together. So this is the dot product of 2, 4 and 3, -1. So you just multiplying them according to its components. So 2 times 3 is 6 plus 4 times -1 is -4, and the answer is going to be equal to 2. Okay, next we have this vector. These are three-dimensional vectors in this representation. So we have, okay, so for question B here, we have vector -1, 7 and 4 times with 6, 2 and -half, and that becomes -1 times 6 is -6, 7 times 2 is 14, plus 4 times half will be -2, and then -6 plus 14, 8, 8 minus 2 is 6. Okay, okay, next this is another three-dimensional vectors represented as the standard basis vectors of I, J and K. So if you want, you can change its representation. There's no problem to that. So if you are more comfortable to work with a different representation, it's okay, just go ahead. So for C, maybe I can change it to simply 1, 2 and -3 multiplied with I is going to be 0 because there is no component, there's no I vector here, and this one is going to be 2 and this is -1. So just multiplying like what you have done previously. So 1 with 0 will be 0, plus 2 with 2 it's going to be 4, plus -3 with -1 it will be going to be equal to 3, and the answer here is 7. Okay, next let's look at some properties of the dot product. So if A and B and C are vectors, okay, and C is a scalar, then the first one is you have the dot product of the same vector, so a and a, the answer will be the magnitude of vector a squared. Well, it is not difficult to see why that is true. This is quite easy to see. If you see you have vector a, let's say you have a three-dimensional vector, which is a1, a2 and a3. This is vector a, okay, times with vector a, the same vector, which is u times itself, so it will also have the same component a1, a2 and a3. And according to the definition, or according to the formula, you can multiply them according to its respective components. So here you will have a1 times with a1 plus a2 times with a2 plus a3 times with a3. And this can be simplified as a1 squared plus a2 squared plus a3 squared. You can see that I can manipulate this statement here so that it looks like this. So we have a1 squared plus a2 squared plus a3 squared, and you square it. So by doing that, I'm actually having or doesn't change. I'm not changing anything. So by having this square root and then squared outside, I'm actually having the same statement as above, just that I'm manipulating this by introducing the square root and the squared at the same time. So by doing this, I'm not changing anything as you see here. And because of that, I can say that this is the definition of finding the magnitude of vector A. So this is actually equal to finding, this one is finding the magnitude of vector A, and this is going to be squared outside. So this is what you have over here. So that's quite easy to see for question 1. So just a simple proving on how you get this one. Okay, so now let's look at the next property here. So this is basically a commutative property. If you have a vector a times with vector b, you can switch the position, b times a, you will get the same result. And for this one, this is distributive, so a with b, the dot product of a and b plus the dot product of a and c. Okay, and this one, if you have a scalar, so c and a, you can either do this first and then multiply it with vector b, or you can actually focus on doing this, get the dot product of a and b and then multiply it with a scalar, or you can also multiply vector b with scalar first and then you multiply with a. Sorry. Next, if you have a vector and 0 is also a vector, then the result is going to be a number. So 0 here is a number. There is a difference between this and this. This is a number and this is a vector. Vector means you have component 0, 0 and 0. This is one single number. Okay, so when you have vector 0 times with vector a1, a2 and a3, the answer will be 0, which is a number and not a vector. This one you can see it by multiplying this, so you get a1 times 0 plus a2 times 0 plus a3 times 0, and the result is 0 plus 0 plus 0, and because of that you just get one single number, which is 0. Okay, alright, I think that's all for now. Thank you very much for watching, and I'll see you in the next video.